Today, I am presenting my project about microwave oven simulation using embedded system. In this project, it demonstrates how a microcontroller can control real-time operations like a microwave. So, overview of embedded system. Embedded systems are specialized computing systems designed to perform dedicated functions, and they are optimized for real-time control. Some of the examples are microwaves, washing machines, and industrial automation devices. A typical C program starts with the header files, definitions, followed by the main function. And it also includes some input and output handling, variable declarations, and a logic for the program. This is the structure of a C program. And the data representation. In embedded systems, data is represented in binary or hexadecimal formats. Efficient data representation is more important for the utilization for memory usage and the speed of processing. And the declaration. Variables need to be declared before use. And the type and size of variables are important to ensure proper memory usage, memory management, and for the processing speed. So input and output, we use printer for the output and scanner for the input. In this project, buttons act as input and the LCD displays act as output. Operators in C. So it is arithmetic operations include plus, minus, and there are relational logical assignment. It helps in calculations and it is used here to handle timers and mode selections in the microwave simulation. Next, coming to the iteration and loops. Loops are used to repeat actions. Single iteration loops execute once, while multi-iteration loops repeat action multiple times. They help in continuously checking button states. Functions in C. Functions allow modular programming. Pass by value sends a copy of the data, while pass by reference allows modifying the original variable. Here, functions manage LCD updates and button handling, which we will further see in the next slides. And the pointers and strings. Pointers are used for direct memory access, and strings help in displaying messages on the LCD. So this makes communication with the microcontroller and peripherals efficient. Coming to the storage class. Storage classes determine the lifetime and scope of variables. Proper memory location is essential in embedded system with limited RAM. Preprocessor directives and macros make the code modular and reusable. They simplify code management in large embedded systems. Some of the predefined macros are file, data, time, name, function. So, coming to the question, what is an embedded system? An embedded system is a combination of hardware and software designed to perform a specific task. It interacts with physical world in real time. General purpose system versus embedded system. Unlike general purpose computers, embedded systems are dedicated, efficient, optimized for specific function. They require minimal resources and operate in real time. Its embedded system can be classified as real-time, standalone, networked, mobile, hybrid. Each type has unique design considerations. So real-time embedded systems, it responds to inputs immediately or within a guaranteed time. Microwave ovens are an example of a soft real-time embedded systems. Coming to the core components of embedded system, it includes microcontroller, microprocessor, memory, input devices, output devices, power supply, software. Memory like RAM, ROM, EEPROM are used. And these are the processing units and the specifications of the microcontrollers are listed here. And the tools used. The tools used include MPLAB IDE for writing and compiling embedded C code, XC8 compiler, PiximLab for simulation. And the host and target. The microcontroller was programmed via MPLAB using the ICSP interface. This allows us to load the compiled hex file into the PIC16F877A. So the programs are the LED blinking program. The purpose is to verify hardware, check tool installation, establish host target connection, and the LED interfacing. So LEDs were used to test basic output functionality. They confirm that the microcontroller can toggle outputs before integrating the LCD and buttons. Switch interfacing. Push buttons act as user inputs. Each button is connected to a specific port pin and changes the mode or starts or stops the microwaves. And the switch detection methods are lever triggering and edge triggering. Lever triggering is a continuous action. Here, the volume button uses a lever trigger. And then edge triggering is a one-time action like power button. Polling versus interrupts. Polling continuously checks the button states while interrupts immediately respond to input changes. For this project, polling is used for simplicity. And the interrupt concepts, we use global interrupt enable, interrupt vector table, ISR, and interrupt flag for this project. Timers are used to manage delays and simulate microwave heating duration. They allow the system to update the LCD at precise intervals. So these are the calculations we used in this project and it is given here. So these are the CLCD introduction and the common size is 16 into 2 used in appliances and it displays all ASCII characters. So it is a 8-bit mode, it is faster and uses more pins and 4-bit modes, but it saves pin and it is used in our project. System architecture. The LCD displays the selected mode and status. The system architecture connects the microcontroller to the LCD and buttons for real-time operation. So, microwave oven project overview. The project simulates a microwave oven. The system reads button inputs, updates the LCD display, and switches between modes. So functional requirements are power on message, cooking mode selection, temperature setting, time setting, start, pass, resume stop, and completion buzzer, and time management, all the LCD updates, mode selection, display initialization, All these are the requirements for the microwave. It has four modes: micro mode, grill mode, convection mode, and start mode. The user selects a mode by pressing the corresponding button. Next, the tools and technologies. The main tools used are MPLab, XCL compiler, and PixelLab for simulation. Embedded C programs used to control the microcontroller. And then project flow. The program flows starts with initialization of ports and LCD, then continuously checks button inputs, updates the LCD, and performs mode operations. And the design approach. The design uses a simple modular approach: input reading, processing, output display. This ensures the system is easy to debug and extend. So what I learned about the microcontroller programming, LCD interfacing, button pulling, embedded C program, and real-time control logic. So this is the simulation of my microwave oven. And this is the code of the program. The LCD will initially display microwave oven. All the compilations have done. So we directly check the simulation part. These are the codes of the program. And this is the microwave oven simulation. The LCD eventually displays microwave oven, indicating the system is ready. And the mode selection buttons are button RB0 is micro mode, RB1 grill mode, RB2 convection mode. It, and the LCD updates in real time to show the selected mode. The system responds immediately to button pushes, demonstrating real-time embedded behavior. This shows how the microcontroller reads inputs and updates outputs continuously. And the LCD changes in each mode. The LCD displays the mode and current operation, ensuring and user feedback, which is crucial in embedded systems. And the simulation is working perfectly. And switching over into the mode and pressing enter. Now it shows the time and it's down counting. In conclusion, this project gave me practical experience in designing and programming an embedded system. I learned how a microcontroller can read inputs from buttons, process the logic in real time, and display outputs on an LCD. And the simulation demonstrated the core functionality of microwave oven, including mode selection, real-time responses, and LCD updates. Through this project, I also strengthened my skills in embedded C programming, debugging, and interfacing. So, thank you for watching my presentation. This project helped me understand how software and hardware work together in real world applications. And I hope it gives you clear insight into embedded systems. Thank you.